Hey, year 10. Thanks for coming, guys. Whoa, look at that. Loads of people suddenly appearing. That's amazing. Let's do the register. Who have I got? Have I got Nick? Wow, Nick, you were the first person here. Respect, dude. Respect. Right. Okay, so I've got Nick. I've got Ashley. I've got Ruby. I've got Moses. Let's have a look. Got Isabel. Got Ruby. Got Moses. Got Con. Got Wen. Yeah, we're smashing this. Got Tong. Got Andy. Got Harris. Man, you guys are on this now. You guys are on this. Got Harris. Got Shanley. Yeah. We got Anna. There's Rue. Yo, Rue. How's it going, dude? Yura is here. Yay. Hi, Yura. Hello. By email. Answer what? I have no idea what that means. Ben's here. Yes, I've got, yeah. There's Victoria, I think. Yeah. Smashing this. I'm missing Anna. I'm missing Toby. And I'm missing Kieran. Is Kieran about? He just doesn't have a channel. Oh, right, yeah. Is that Kieran? Yeah, Kieran is watching. Okay. Thanks very much for that. Why doesn't he have a channel? Just watch it on. I don't get it. Has anyone seen Anna? Haven't got Anna yet. Haven't got Toby. Oh man, Toby was in it yesterday. Where is he now? Huh? Where are you, Toby? He's meant to be the first one here. You know, having my name, it's the least you should be able to achieve. Okay, right, guys, I'm going to crack on. So, first question, is everyone okay? How's everyone doing this morning? Probably procrastinating his monologue. I'm not entirely sure how you can do that. How do you procrastinate a monologue? I'm just going to check my sound, by the way. Got Shanley. Oh, yeah, that's loads better. Yeah. By the way, I've got a new laptop. Woo! So no more shaky screen. Excellent. I take it when you talk about his monologue, you're talking about his drama bit. Oh, dear. Well, show us. What is it? Congrats. We're supposed to film it. Oh, I see. Okay. Right. Okay, guys. So, has everyone had a chance to have a look at the homework? Has everyone managed that one? Moles in solution? Anybody? Love the response. It's such a great response. Oh, funny. Right. Okay. In that case, guys, I'm going to submit the register. Oh, there's Toby. Rocking up. Toby, you're in. I'm registered. Yeah. Somebody let me know when Anna turns up so that I can register her as well. I know that she's having difficulties, I think. I think lots of people have. Great job, Tom. Great job, Isabel. Great job, Shanley. That's awesome. Really happy. Right. Let's share the screen. Let's crack on with today's lesson. There we go. Right. So you guys should now be able to see my screen. Cool. So today's lesson is going to be on moles in gases. But before I do that, I want to go through the questions on moles in solution. Definitely something I want to go through. All of these, I like going through the worksheets. They do, I do see value in this. So let's have a look. So it says, calculate the concentration of the solutions in moles per dm cubed. So the first thing I think we need to recognize is, I'm just sorry, hang on. My pen's having some issues. That's so typical. Oh. Definitely having issues with the pen. Okay, hang on a sec. I've got a different pen. Let's give this one a try. Maybe the battery's gone. Totally possible. There we go. So moles, we've been given moles, we've been given a volume. So number of moles is C times by V over 1,000. First question, why am I over 1,000, folks? Why am I not using the original equation of C times V? Which part of the question tells me that bit? Just gonna wait for the first response. Okay, so which part of the question, Rue? You said Diem cubed for the concentration. Oh, okay. Yeah, I don't mind that response. Yeah, recognition that the concentration that we have been asked to actually provide is in moles per Diem cubed. Oh, do you notice that my moles per Diem cubed? But in reality, of course, it's because I've been given centimeters. They're going to agree with that statement. Yeah, so I'm now going to lob in my numbers. My moles, I have got moles, that's that bit, and I have got volume. Right, we need to reorganize the equation, folks. Moles times 1,000. Yeah, so I brought the 1,000 up and then bring the V down. So all over V will give me C. So there's my rearrangement. I always think you should always do the rearrangement every time. It's just really good practice. So then we can lob in our numbers of 0.1 times by 1,000 all over 200. Run that through on my calculator. Now I can do that in my head, but I'm not going to. Yeah, I know that I see students pick up a bad habit of because they can do these things in their head. They constantly end up making silly errors. So we've got 0.5 moles per Diem cubed. Tick it if you got it correct. Fab. Next thing, 0.2 moles of sulfuric acid in 100 centimeters cubed. Do you know what? At this point, what I'm actually going to do is I'm going to put my equation somewhere so I can keep using it. I don't like triangles. Ignore that. Yuck. Yeah. Number of moles times 1,000 divided by V gives me C. Right, there's my equation. So just going to lob in my numbers. So my moles is 0.2, my times 1,000, and my volume, of course, is over 100. Now that 100 cancels out with two of those, so it's like times by 10. So that's going to be 2 moles per Diem cubed. I'm going to check it on my calculator anyway. I always have to. I just don't care how good I am at maths. I'm always going to do it, and that is correct. Next, so 0.02 multiplied by 1,000 divided by a volume of 25, and I get 0.02 times by 1,000 divided by 25, and I get a concentration of 0.8 moles per Diem cubed. There we go. I like it. Next. Question number 2. So I'd love 0.5. Oh, was that you talk about the first one, Shan? Have I made a mistake? Don't know. I'll come back to you in a sec. You can give me a bit more detail, Shan. Calculate the number of moles of the following. Oh, this one's nice and easy, isn't it? Number of moles is C times by V over 1,000. We're using 1,000 because we're in centimeters cubed in the question. Yeah, that's what I'm constantly trying to force here, folks. So the concentration 0.2 of 100 all over 1,000. So that's the same as that cancelling out. It's the same as a divide by 10. So it's going to be 0.02 moles. I'm just going to check that anyway. Yeah, so 0.2 times by 100 divided by 1,000, 0.02. We're good. Yeah, note for question 1. Okay, cool. Next, same thing again. Number of moles is C times by V over 1,000 because we're in centimeters cubed in the question. So the C is 1.5 because that's the concentration. We recognize our units times by a volume of 25 all over 1,000. So I'm going to do 15 times by 25 all over 1,000 gives me 0.375 moles. I hope you guys realize that these worksheets in reality shouldn't take you. I'm not trying to set you guys homework every day that's going to take you hours and hours. I'm really not trying to do that. I'm just trying to give you these simple, quick worksheets to reinforce good practice and to have an opportunity to see questions. So the next one, number of moles equals C times V over 1,000. I feel like I want to reduce my pen size. There we go. So concentration is 0.1 multiplied by a volume of 50 all over 1,000 gives me 0.1 times by 50 all over 1,000, and I get, oh, that's interesting, 5 times 10 to the minus 3 moles. Now, by the way, I love calculators are so, oh, have I made a mistake? Oh, I think I may have. 50 multiplied by 25 over 1,000 gives me, oh, Shan, wait, shouldn't it be, just run your maths again on that. That's what I mean by these, have I made a mistake somewhere? Oh, I have. I've missed the decimal point out on my calculator. Thank you, Shan. 1.5 times by 25. Oh, by the way, I've just found out, I've just noticed that on my calculator, I've got a dodgy decimal place button. Can I just say that one of the I shouldn't say pet peeves, it's the wrong word. Thank you, Shan, for being on the ball. Thank you. And that's how easy it is for anybody to make a mistake. Yeah. And that just shows me my decimal place button is sticky. I don't know what I've spilt on my. Now I know that, I'm going to bear that in mind. This is why if you show up to an exam, folks, without your own calculator, you're not going to know how it behaves. You need to learn your calculator and learn it well. Yeah, it's so, so important. I'm just going to quickly mention this one as well. This 5 times 10 to the minus 3. There's a little button on your calculator called eng. So if I type in 5 exponential minus 3 and do eng, or do shift eng, do it twice, it'll take it out of standard form for you. That was one of the most useful things I have ever discovered. I had to do it twice, by the way. I did shift eng, and then it did it. I don't know why it does that, but it does. Ever to go from standard form on a calculator, standard form of 5 times 10 to the minus 3. Yeah, I've just done shift, shift eng, and it looks like this. Mine's all in capitals. Shift eng, and I did it twice. Yeah, I did shift eng. I did it again, and then it dropped it out of standard form. If you then just do eng, it'll take it back into standard form. Yeah, I did it twice. Have a go at it. Super useful. I discovered this trick because the students in my class, some of them don't like working in standard form. And so what they kept on doing is they kept on trying to change it out of it and were making silly mistakes by losing decimal places because they were hopping zeros. And I was like, guys, your calculator does this for you. And when I showed it to them, they were like, oh my God, you've changed my maths world. Because apparently in maths, they constantly require you to shift in and out of standard form. So what a useful thing. By the way, if you just type in 25 and then do eng and then do answer and then do 25 equals and then do eng, it'll put it into standard form for you. It's really handy. I really, really like it. It's one of my favorite tricks on the calculator. Anyway, just thought, okay, you can play around with that. Okay, next. Calculate the concentration of the solutions in grams per dm cubed. Okay, so this requires a bit more work. So what we need to do is we've been given moles per dm cubed and we need to get to grams per dm cubed. So what that means is we need to go from moles per dm cubed. This is where my laptop's being a bit sticky now. Moles per dm cubed. And we're now dropping it down to grams per dm cubed. Now, what I want you to notice is that the decimeters hasn't changed. What that means is all I actually need to do is convert moles into grams. So here's my equation. Number of moles is grams over rams. Right, now that it's grams over rams, I need to reorganize because I'm after grams. Bring rams up. So times both sides by rams. Yeah, and I end up with grams. So all I actually need to do is multiply the concentrations by the relative molecular masses. So the question is, what's the relative molecular mass of sodium hydroxide? So that's going to be a 2-mark question, 2 marks at GCSE. So the first thing is sodium, of course, on the periodic table is 23. Oxygen is 16. Hydrogen is 1. Total numbers, 40. So the relative molecular mass of sodium is 40. I'm going to multiply 40. So 40 multiplied by 0.1 gives me, it's the same as divide by 10, isn't it? Times by 0.1. So that gives me 4 grams per Diem cubed. If you then had to change a volume, you just do it in a third step. So don't ever worry about it. Right, next. By the way, if you weren't sure on these questions, what I could now get you to do is, can you pause the video and have a go at B and C for me? That would be really handy, because what you're doing is you're taking the new bit of information that I've just got from the previous question, and I'm getting you to apply it, and that way it'll help fix any of that broken data. Okay, so now that you've paused it, you can unpause it. So the first thing I need to do is I need to know the relative molecular mass of vinegar. So that's vinegar, by the way. That's ethanoic acid is what that is. It's a family you learn at GCSE. So, okay, number 1, I've got carbon. Yeah, carbon is 12, but there's 2 carbons in it. So times 2. I'm going to add that to hydrogen, which is 1, but I have 4 of them. So times 4. And then I'm going to add it to oxygen, of course, which is 16 from the periodic table, times 2. So I'm now going to get 12 times 2 plus 4 plus 16 times 2. And I get an answer of 60. First mark, tick. Next. So now I'm going to do 0.250 multiplied by 60, and I'm going to get times 0.25, and I get an answer of 15 grams per Diem cubed. I like it. Next. Okay, now we're doing exactly the same thing. Now I've got to work out the relative atomic molecular mass. Mr. Duncan, why isn't it that O instead of O2? That's a really... Ashley, thank you so much for asking such a great question. The reason being is, now, in organic chemistry, in organics, now organic chemistry is all about carbon. In organic chemistry, you deal with a whole load of different types of formulae. And that formulae, so we've got obviously a displayed. This is the one that you learn in organics for GCSE. You learn this one heavily. This is called a displayed formulae. Now, a displayed formulae has a definition of showing all bonds. And I'm going to capitalize the word all. So, by the way, the most common mistake at GCSE is for students to do this. I don't know where you get it from the internet. The internet's great to a certain extent, folks, but the problem is it does have some bad chemistry on it. So that's not a good answer, that. So that's ethanoic acid. We then get a molecular of C2H4O2. That's a molecular, a formula showing the actual numbers of each element in a compound. And then you also have what's called a structural. And a structural formula you have to show in certain ways. And this family here, that structure there, is the structure for a carboxylic acid. And it's what makes that molecule, it's what gives it all of its properties. And the way that that's written in structural is like that. Cool, it's a pigeon. Yeah, all the carboxylic acid are pigeons in structural formula. So that's why. Good question, though. Next, so we're going to work out what the relative molecular mass of nitric acid is. Hydrogen is 1, and there's only 1 of them. I'm going to add that to nitrogen, which is 14, and there's only 1 of them. And then I'm going to add it to oxygen, which is 16, and that's times 3. So we're going to come up, I have no idea what nitric acid is. Haven't got a clue. 1 plus 14 plus 16 times 3. 63. I never use it. It's such a rare one. Yeah, now, of course, I just need to do my usual trick. 1.5 multiplied by 63, and I'm going to get 1.5. I'm really hitting my decimal place button now. 1.5 times 63 gives me 94.5 grams per dm cubed. There we go. That's actually quite a lot, that. But it is quite concentrated. Yeah, I mean, the highest concentration of nitric acid, I think, goes up to about, I think it's 7 moles per dm cubed. Anyway, so cool. Next. Okay, now we're being asked to put it into concentrations. So we need to rearrange our equation. You never, ever, ever learn a rearrangement. You just learn one equation and learn how to handle it. I'm looking for concentration now, folks. So I'm going to multiply both sides by 1,000. I hope you guys realize what I'm doing here. I'm trying to show you guys all the mathematical methods of rearranging equations. Yeah, so I've times both sides by 1,000. Then I'm going to divide both sides by volume. Yeah, and that way it cancels on that side. So there's my equation. There we go. Gives me concentration. Let's now run our numbers in. So I've got 1,000 multiplied by moles. So moles, of course, is there. So I'm going to multiply that by 0.2. Divide it by the volume. The volume is centimeters cubed, so I've still got the 1,000, still needs to be there. There's the volume. Shouldn't do that in that color, should I? There we go. So the volume's going to go in at 250, right? And then just run it through, and I'm going to get moles per dm cubed. 1,000 multiplied by 0.2 divided by 250. Gives me 0.8 moles per dm cubed. I like it. Next. Calculate the concentration in grams per dm cubed. Oh, well, that's nice. We've already worked out the relative molecular mass of sodium hydroxide, and I think that was 60, right? Or was, yeah, 60. There you go. Oh, no, 40. It's 40. Lol. So now we do 0.8 multiplied by multiplied by 60. It was 60. Was it 60? No, 40. Darn you. I don't know. Sorry, folks. Divided by times by 40. Yeah. So I'm going to get 0.8 times by 40, and I get 32 grams per liter. I like it. Next, 5 grams of potassium nitrate in 100 centimeters cubed of water. Right. They've done something clever here, folks. Look, they've given it to me in grams. So what that means is, if I were to run this straight through, yeah, if I were to run this through concentration, well, I'm actually going to spit out grams per dm cubed. This whole idea of number of moles is C times V over 1,000. Yeah? Well, you've got two choices. Some students don't like these kinds of questions because if they feel uncomfortable doing it. Well, if you want, just use the original equation and convert to moles straight away. So in my steps now, I'm going to go, okay, so I've got 5 grams of that. So number of moles is grams over rams. Let's do that first. So that's 5 over potassium nitrate, 39 for potassium, plus 14 plus 16 times 3 is 101. So 5 over 101 is going to give me it in moles, which is 0.0495 moles. Right now, I can put that number into here. Reorganize for concentration. So I'm going to multiply both sides by 1,000. That one vanishes. Divide both sides by V, disappears, and I get C. So what's now going to happen is, guys, I'm going to be spitting out moles per dm. I'm doing B before A. I hope you all recognize that. So I'm now going to do 0.0495 multiplied by 1,000 all over a volume of 100. So times 1,000 divided by 100. And that gives me a concentration of 0.495 moles per dm cubed. Now I can convert that to grams per dm cubed by multiplying it by the MR again. So I can now do 0.495 multiplied by the MR, which is 101, and I get, times by 101, and I get 50 grams per centimeter cubed. per liter per decimeter cubed. There we go. Now, I just want to quickly show you another way of doing that, because some students would be like, that seems like a long way round. Well, the reason why I don't like teaching this, folks, is because number of moles is C times V over 1,000. I think everyone agrees with this now. Well, let's just consider this for a minute, folks. If I put in moles here, yeah, if I put in moles, that means I'm going to get moles in the concentration. That's going to therefore give me moles per liter. Well, if I did that. Now, can I just point out, I don't want you to learn this, folks. This is a massive leap in understanding. Yeah, and I'm very, very cautious of this. But if I put in grams here, then I'm going to get a concentration in grams per liter because the volume is in Diem cubed. In this case, of course, it's not. It's in centimeters cubed, but the divide by 1,000 causes it to be so. So I could have just done grams times 1,000 over the volume of 100, and I would have got a concentration in grams per Diem cubed. I don't want you to learn this, folks. This is a huge leap of faith, and most students really struggle with that. I have one task here, and that is to get C times V over 1,000 into your head. That's what I need to do here. So if I'm just going to run it through anyway. Yeah, and I get the same answer. If I put in 5 here, I get the same answer of 50 grams per liter. I'm just saying, but it depends how solid you are on maths and your understanding of solutions is. I don't want to make this too complicated. Yeah, just bear that in mind. I'm just throwing out another option here, folks. That's all. That brings us to the end of the worksheet. So how long did that take me? It took me, I've been doing 26 minutes. That's quite a long time, to be fair. So, but I was trying to do an awful lot of explanation there along with bits and pieces. So anyway, if you guys would like, if you've really struggled with that, I've got another sheet of questions with solutions on it. So if you want another one, send me a message on the chat, and I'll put another one on the classroom for you to have a go at. Right, title for today's lesson, folks. Titles for today's lesson. I don't know if anybody can tell what it is. There we go. I'm attempting to draw a balloon. I wonder if you guys can figure out what I'm trying to draw here. Really struggling. My new Surface has got a super shiny screen, and I'm not really entirely used to it yet. Not entirely used to it. Oh no, I don't like that bit. There we go. He's nowhere near as good as my other one. There we go. Yeah, it's in a gas. This is a mole in gases. I am so weird. I'm going to give him a bit of fur. Let's make him a bit furry. There we go. There we go. Furry mole. There we go. Yay! It's a mole in gases. He's in a balloon and he's floating around. That is 1 mole in gases. Title is moles in gases. Oh, so funny. Anyway, so just to reiterate, we've been picking up equations so far, and we've already got 2. We've got moles is grams over rams in solids. Yeah, I've then got moles is C times V over 1,000 in solution. And we now pick up a new one, which is moles is V over 24. So this is called this is the gas equation for moles. Now, just to let you know, I've got to have V in a particular unit to get this, and that's going to be in Diem cubed. So if I measure gases in liters, I get V over 24. And I don't quite understand Edexcel's thinking in this, folks, because that's actually really unusual to use. Chemists don't measure anything in liters, ever. The only thing we ever measure in is centimeters cubed, because otherwise it's just madness. It's madness to try and measure anything in liters. So what would this look like if I had gases measured in centimeters? Number of moles is V. Honestly, I'm really struggling with my new tablet here. It's because the screen's so shiny, as I said. It's V over 24,000. Yeah. If you've got centimeters cubed gas, which is probably more likely, if I'm going to collect a gas, I'm going to be collecting it not in liters, but in centimeters cubed, because that liters is a lot. What gases am I going to be trying to generate that are going to be making liters? It's very rare for me to do so. Madness. Anyway, so we've got a new equation, and what that means is we just simply need to use it, which is not overly complicated. It's a nice simple equation, 3 pieces. I do not want to see you guys using triangles. Please don't. It's one of my pet peeves. Sorry, guys, and I really, really do want you to try and avoid it as best as possible. Okay, so I want to explain now why 24. Thank you, Rue. Why 24? So, question, why 24? Okay, I can tell you why, Rue. It's because about 200 years ago, a very famous chemist called Lavoisier. Now, this guy was obsessed with gases. And he was just making gases for fun, lots of different ones. Oxygen gas, nitrogen dioxide, hydrogen gas. And he was just playing around with them. And he made a very unusual discovery. He discovered that if you have balloons, now I obviously can do this, you guys can't. I want to do, oh, maybe I can't either. Copy, and then I want to go paste, le paste. Right, let's move that guy over to here. And then I'm going to go le paste, and then put him here. What he discovered, Rue, was if you make different gases. So I've got a balloon. I have a balloon of hydrogen. I have a balloon of carbon dioxide. And I have a balloon of NO2. So let's just check the weights of each of these particles. So hydrogen, of course, on the periodic table is 1, but it's in a pair. So I'm going to times it by 2. The relative molecular mass of hydrogen is 2. Carbon dioxide is, carbon is 12, there's one of them, plus oxygen, which is 16 times 2, MR 44. Nitrogen dioxide is 14, and then we've got 16 times 2. I have no idea what that one is. It's too heavy. So that's 46, I believe. I think so. And what he discovered, we can even have a balloon of helium if you like. You can even go that way. You can even go even lighter than this. Actually, technically, hydrogen is the lightest of all the gases, just so you know. I'll show you why. If I go for a balloon of helium, which all of you recognize, yeah, you all recognize helium. Helium, of course, on the periodic table is 4, which means a balloon of helium is actually twice the weight of a hydrogen balloon. That means if you wanted to actually float up, if you wanted to tie these things to a basket, yeah, if you were going to tie these things to a basket and then, you know, float up into the upper atmosphere, yeah, the best balloon that you could use would be a hydrogen balloon. And it was actually the very first flying machine. First done by the French, actually. They had a big festival where they actually launched balloons using hydrogen gas. It was amazing. Even before hot air... Oh, no, hang on a second. No, I tell a lie. I think hot air balloons came first, but hydrogen balloons did come second. And it was very close, actually. I've suddenly realized what I need to put in the basket. I'm going to put a mole in the basket. Let's see if I can put a mole. I'm going to have to zoom right in for this. My pen's too fat. There we go. There's make my pen a bit thinner. I should. Oh no, I can't. It's already as thin as it gets. There we go. There's my little mole in the basket. Sigh. Oh. So there we go. So if that's technically the lightest of all the balloons, but what did Lavoisier discover? He discovered that if you have 1 mole of any gas in a balloon, it has the same volume. So 2 grams, let's put 1 mole in each of these. I'm going to put in 2 grams of hydrogen. I'm going to put in 44 grams of CO2. I'm going to put 46 grams of NO2. I'm going to put in 4 grams of helium. So all of these have 1 mole because 1 mole is its MR in grams. 1 mole of any gas occupies 24 Diem cubed. Isn't that magic? Now, if there are anybody in this room who wants to know the reason for that, I can explain it, but it is physics. I can explain that. But as I said, you do not need it for chemistry in any way, shape, or form. It's more of an A-level extension, really. It's to do with the fact that it's the temperature that actually decides the size. If, by the way, just to tell you, by the way, of any gas is 24 Diem cubed, I'm also going to put at 25 degrees Celsius. That there is room temp. Room temperature. Yeah, room temp. And that's so they have to be at 25 because we know that if you heat up a gas, it'll expand. If you cool down a gas, it'll shrink. So they all occupy 24 Diem cubed at room temperature. Now that's magic. What that means is we can use this as what's called the ideal gas constant. By the way, it is a gas constant, not the ideal one. So this is called a gas constant. Cool. Amazing. Isn't that cool? So now that we kind of understand that, we can just start looking at questions. And this is really easy. So question number 1, folks, for you guys to have a go at. I want you to have a go at the question. Pause the video when you have a go at it. And then you can then check your answer. So question, how many moles of CO2 are there in 250 centimeters cubed of gas? I like it. So don't overthink it, guys. The first thing that you'll do, so can you please pause the video, have a go. You can have a look at your notes, use your notes, yeah? But remember, so here's your answer once you've unpaused it. So we've got number of moles is V over 24, but that requires me to be in Diem cubed. So I'm now going to say, therefore, number of moles is V over 24,000. Okay, now that's centimeters cubed. That's what I'm working in. Yeah, that was in the question. So that now gives me this equation. Yeah, I like it. So now all I have to do is put in my numbers. I don't even need to know the MR. All I have to do is simply go to put 250 over 24,000, and I'm going to get 250, calculate 250 divided by 24,000, and I get 0.0104 moles. That's easy. That's literally as easy as it is. Right. Are you ready for question number 2? Okay, question 2. Again, pause the video, have a go at this. Give me some feedback if you want me to do anything else. Okay, next question. So, what volume does let's go for what volume does 0.6 moles of nitrogen, what volume occupy in centimeter? Let's go in liters. Let's keep it easy. Give your answer in decimeters cubed. Yeah, right. So, number of moles, answer. Pause the video, fill it in, please. So, number of moles is V over 24. Don't ever learn a rearrangement. Learn one equation and learn to rearrange it. Yeah? So, bring that. So, therefore, moles times 24 gives me volume. So, add my numbers in, 0.6 times by 24. 0.6 point, taking my point away again, times 24 gives me 14.4 decimeters cubed. Dead easy. Not complicated. Right. Is everyone thinking on this? Yeah, I can do this. Let's make it harder, shall we? Right. I'm going to help you out now, folks. Number of moles is grams over rams. Number of moles is C times V over 1,000. So this is for solids. This is for aqueous. This is for gases. V over 24 for gases in Diem cubed. Just to tell you, by the way, moles or grams over rams can be used for anybody, liquids, gases, if you've been given grams. If you're given grams, you use grams over rams. It's not complicated. So, question. I have 10 kilograms of liquid nitrogen. That's how much I buy, guys. Liquid nitrogen. What volume of gas would it occupy? Go. That is much, guys. This is an A-level extension question, really, for a GCSE class. That's A-level. That is not GCSE. It is much, much, much harder than GCSE, that, folks. They have never done it. So I'll just want to keep that in mind. That would be great. Have a go. Okay, are you ready? Much harder. I have been given kilograms, which means the first equations I need is that one. So number of moles equals grams. I need to do a conversion. 10 kilograms is equal to 10,000 grams. I've got to do that conversion. So grams over rams over nitrogen. How much does nitrogen weigh? Nitrogen on the periodic table is 7 and 14. The top number is what matters. It's in a pair, so it weighs 28. So grams over rams, 10,000 divided by 28 gives me 357 moles to 3 sig fig. Right. Now I've got moles, I can use any of the equations that I want. And I'm now going to use this one. So I'm going to reorganize for volume. I'm going to do moles times 24 gives me V in decimeters cubed. So I'm now going to go number of moles, 357 multiplied by 24 gives me a volume of 357 multiplied by 24, and I get 8,568 liters. Isn't that amazing? From 10 kilograms. Yeah, so by the way, 10 kilograms is essentially 10 liters. It's not quite actually because the density is slightly different. But guys, from a volume of this big, you know, like 10 liters, give or take. Yeah, 10 no, I don't like liters. That's squishy biology units. From 10 decimeters cubed as liquid nitrogen. Yeah, I'm now going to get 8,500. Holy moly. Isn't that mental? That's crazy, all because I've now formed N2 gas. Isn't that bonkers? It just shows you, by the way, we never, ever, ever store gases as gases. Whoa, that's so cool. I know, right, actually? This is why, if you buy a gas, yeah, we store it as a liquid. We cool it down, liquefy it, and store it that way, because we take this huge volume and turn it into the itty bitty volume. Yeah. So amazing stuff. And it's just, it's so nice to have these simple equations. Right, guys, that brings me to the end of my lesson. How amazing is that? It's been a great lesson. Really enjoyed it. Let's see if I can get back to... I've just taken it away. Ah, there we go. Yo, we're back. Guys, thank you so much for coming. I'm going to post on the classroom. Yes, I know we still have 10 minutes. In fact, I've done that. If it turns into gas, would the container explode? Oh my God, yes, Isabel. That's actually one of the main problems that we have. One of the biggest problems that we've got with gases is because we store them in bottles as liquids, if you heat them up, then the containers can explode. You've got to be super careful with gases because obviously if the really careful. Okay, so I'm going to post on the classroom, folks. I'm going to post on the classroom the gas questions. I want you to have a go at them, and I'll see you guys next week. Have an amazing weekend, guys. Stay safe. I miss you all. I'll see you soon. Bye now.